Hi, my name is Alexander Liu from National Taiwan University. I'm here to present our paper Sequence-to-Sequence Automatic Speech Recognition with Word Embedding Regularization and Fuse Decoding. Okay, so let's begin. I'd first like to talk about our motivation. Our goal is trying to utilize unpaired text in attention-based sequence-to-sequence ASR training. So unpaired text is generally more easy to collect comparing to the audio and transcription paired data. So we would like to take the unpaired text together with word embedding algorithms and to obtain the word embeddings. And then we collect the paired data and word embedding together as training data to train our sequence-to-sequence ASR. So here's a paradigm of sequence-to-sequence ASR. It's usually composed by an encoder, an attention module, and also a decoder. And we'll be focusing more on decoder and later in our methods. So before we go into our method, I would first like to talk about why we select word embeddings as the target. So first of all, word embeddings are generally more easy to obtain, and there are already many off-the-shelf solutions that is available. And next, word embeddings are designed to be more contextually meaningful, and we would like our ASR to learn those contextual informations from the word embedding vectors. And finally, we will want our method to have less additional computation cost on ASR training since the word embeddings are usually pre-trained. So let's first take a look at standard sequence-to-sequence ASR training. So for each time step, the ASR decoder will output a distribution over the vocabulary. And let's say for this time step, the target word is how. To train the ASR, we will need to minimize the cross entropy between the decoder output distribution and the one-hot representation of the word how. And this goes on for each time step to train the ASR. And the question now is, can we use word embedding as target instead of one-hot representation of words? So this is what it looks like if we set the word embedding as the target of sequence-to-sequence ASR. So for each time step, the ASR decoder will output a vector, and our goal now would be maximizing the cosine similarity, which we know that C is here, between the decoder output vector and the target word embedding vector. So this also goes on for each time step, and we hope that the ASR can be trained in this way. However, this failed terribly in practice. So now the question is there a better way to use the word embedding? So here's our solution, the word embedding regularization. So again, for each decoding time step, the ASR decoder will predict an output vector. And just as we demonstrated in the standard sequence-to-sequence ASR training, the output vector will be used to derive the probability distribution over the vocabulary set. And this probability will be used to minimize the cross entropy, just as we said before. But at the same time, we would also like the output vector to be used to predict the word embedding. And this predicted word embedding will be used to maximize the cosine similarity against the word vector from the pre-trained embedding table. So now we are bringing back the cosine similarity just as a regularization term. So for training sequence-to-sequence ASR with word embedding, especially as regularization target, we're now rewriting our learning objective as minimizing the cross entropy, meanwhile maximizing the cosine similarity with the regularization weight lambda. And since this is just a regularization method, for decoding, we only need the probability prediction here, and we do not need the word embedding part here. So now again, we're trying to ask, can we do more on word embedding even during the decoding stage? This is the second proposed method called fuse decoding with word embedding. So the goal now is to that the output probability be corresponded to cosine similarity to each word embedding. Here we have the figure from the previous slide with predicted distribution, predicted word embedding together with the targets. We first define a new probability distribution based on a softmax function. The softmax function takes cosine similarity between each entry of the word embedding table and the predicted word embedding as input. So this distribution will be completely based on cosine similarity. And we have another distribution that is directly predicted by the ASR decoder. We will take the weighted sum of the two distribution with a fusion weight lambda to obtain the fused distribution. And this is the final output probability that is used to maximize the cross entropy. So as you can see, in this case, the word embedding can be involved in the decoding process and contributes to the fused distribution. And this is pretty much all the proposed methods in our paper, but I'm skipping some technical details due to the limited time, and please refer to our paper if you are interested. Alright, moving on to our experiment. I'll first go through some settings of our experiment. The dataset we're using is the clean speech from LibreSpeech as the pair data, and for the unpaired text, we use the transcriptions of the rest audio in LibreSpeech. And here are some implementation details of our model, and I would like to highlight that the regularization weight we mentioned before is set to 10, and the fusion weight is for similarity-based distribution is set to 0.1. So the first experiment is running on a high resource setting. In this setting, we have 460 hours of pair data. For the unpaired text, we use the transcription of the other 500 hours of speech. These unpaired texts are used to train the word embedding as well as the language model. Our baseline model here is the standard sequence-to-sequence ASR. This model performs around 14% of word error rate on testing set, and the number can be reduced by around 2% when a language model is involved in the decoding process. So the first thing we want to show is that our proposed word embedding regularization method provides around 10% of relative improvement in terms of word error rate. And notice that this is similar to the improvement you gain from a language model. Second, the choice of the word embedding algorithm does matter. As you can see, when we are using BERT as our word embedding algorithm, we have the best performance. And if you switch the word embedding into CBOW, you can see the performance dropped significantly. Finally, there is a consistent improvement when combining our regularization method with joint language model decoding. So this means that our method can be combined with other decoding method and the performance is gained by our method stands. For the second experiment, we are running on a low resource setting. In this setting, we only have 100 hours of pair data. Notice that this is a quite limited situation for sequence-to-sequence ASR. And for the unpaired text, we have the transcription of the other 360 hours of speech. And again, these transcriptions are used to train the word embedding as well as the language model. So the baseline is still the standard sequence-to-sequence ASR model, and this time the performance on testing set is around 22% of word error rate. And when a language model is involved, this number can be reduced by around 2%. And so our first observation is that the word embedding methods improve the word error rate by 1% when pair data is really limited. And this improvement is made by the fused decoding method. And the second observation is that there is still a consistent improvement when language model is involved. So again, you can stack our method together with other decoding method and the performance gain is simply added. So here, these are just some quick highlights of our experiments, and for more detailed study or comparison against other methods, please refer to our paper. Some takeaways. In this paper, we proposed a new regularization method for sequence-to-sequence ASR. And our method allows ASR to take benefit of additional text source and powerful off-the-shelf word embeddings. Our method is lightweighted. This means that the improvement we gain is just using a small computational price. Finally, our method is compatible with all existing decoding techniques. This means that you can just use them all to get the best performance instead of choosing one. So this is the end of my presentation, and the source code of this project will be available through the QR code if you are interested. Thank you for your attention.